Okay, so next we are going to learn about the analysis of LTI systems using Laplace transform. Okay, so what is LTI system? LTI system is linear time invariant system. Okay, that is a system that has the property of linearity and also it is time invariant. Such a system is called as LTI system. Okay, so one of the benefit of LTI system, one of the characteristics of LTI system is that we can take, for example, let me just draw an LTI system. Let this be a circuit, any symbol circuit. Okay, so let this be an LTI system. Okay, that is, it has the property of both linearity and time invariancy in this system. Okay, so in this system we know that for example, let we take x of t as my input. Let x of t be the input of the signal. Okay, and let y of t be the output of the signal. Okay, the output of the signal. Okay, so in order to get the output from the input, then every LTI system has a unique function called as h of t, and this h of t is called as the impulse response. The impulse response, that means that if I'm saying in short, x of t, right, this x of t is what you call as the input, or also called as the excitation. Also called as the excitation. And this y of t is what you call as the output, or it is also called as the response of the system. The response of the system. And this h of t is a unique value. It's a unique function which is only unique to that particular type of system. And this h of t is what you call as the impulse response. So the thing is that for any system, if you know the x of t and if you know h of t, then you can simply find the equation for y of t. That is, y of t is nothing but the x of t convolution with h of t. This is how you define the equation for that particular system. That is, if you can find the output of any LTI system as long as if you know the input and if you know the impulse response which is unique for that particular LTI system. So this is how we define the LTI system, by this equation, right? We have already learned this equation. This equation is defined by the fact that this is nothing but 0 is equal to integral minus infinity to plus infinity x of tau into h of t minus tau d tau. So previously you have already learned about problems finding the convolution, that is using the time domain method, right? X of tau into h of t minus tau, right? So this is how we find the output of the signal or the response of the signal, by using this equation. Okay, but one of the benefit of Laplace transform, right, one of the benefit of Laplace transform is that in order to find the output, you don't need to apply this very difficult equation. You don't have to apply this equation. This equation becomes even more simpler if you are using Laplace transform. That is one of the benefit. You know the convolution property. Like for example, when I say let this x of t, right, so let the Laplace transform of x of t be x of s. Okay, let the Laplace transform of the input signal be x of s. So this is the input function. X of s is the input function. Okay, and let the Laplace transform of y of t. This Laplace transform of y of t is equal to y of s. Okay, so this is the Laplace transform of the input signal and this is the Laplace transform of the output signal. Okay, and let the Laplace transform of h of t be defined as h of s, with the Laplace transform h of t is equal to h of s. Okay, so when we say according to the convolution property of Laplace transform, according to the convolution property of Laplace transform, y of t is equal to x of t convolution h of t, right? So if I apply Laplace transform to this equation, then all I need to write is, this becomes y of s is equal to x of s into h of s. You see, if you are using Laplace transform, then you need not apply the convolution to find the convolution of that operation. All you need to do is find the Laplace of x of t, find the Laplace of h of t, and then multiply these two functions. That's all. Multiply these two functions. This is how we find the Laplace. This is the main advantage of Laplace transform. That is, in all the previous modules, every chapter that you have learned before this, using this convolution equation was a very difficult equation. You have to write a lot of steps. You have to find the value of the tau value, the range of tau and the range of t in order to satisfy this equation, and then finally you have to find the value of y of t. This is how you did this equation. That's why the convolution problem is a very difficult problem, right? But when you are applying Laplace transform, then this equation becomes more simpler. Yes, you don't have to apply any integral or any convolution method. All you need to do is simply find the Laplace transform of the two signals, and then finally you just simply multiply the signal in order to find your output. And then to find the input, find the inverse of this. In order to find y of t, find the inverse of this. Right? If you want to find the output signal, find the inverse of this. This is how we do the problem. Right? So that means basically everything that you have learned so far, that is every convolution problem that you did so far, was actually in a way is actually useless, because if you know to find the Laplace transform, then this question becomes very easy. Simply multiply those two Laplace transform functions, then your problem will become very easy for you, right? And one of the characteristics is that this h of s that you see here, this h of s that you see here, this h of s is called as, you have already know about this, you have learned about this. This is called as your transfer function. Transfer function. So in other words, what is h of s? In other words, I can say that if h of t is the impulse response, then the Laplace of h of t, which is h of s, and this h of s is called as your transfer function. Transfer function, right? Because we know what is transfer function is. Transfer function is basically nothing but we are actually dividing the frequency domain of the output by the frequency domain of the input, right? That's what we see here in the last time. Here, if you see, if I write y of s is equal to x of s into h of s. So in other words, what is h of s? H of s is nothing but y of s by x of s. That means if you want to find the transfer function of any LTI system, all you need to do is take the Laplace transform of y of s and divide that with Laplace transform of x of s. And that's your equation. You see, this is how your problem did. So every problem becomes very easy once when you know to find the Laplace transform and then when you take the inverse. Simply apply this equation. If you want to find y of s, multiply x of s with h of s. If you want to find the value of h of s, simply divide y of s by x of s. Right? So this is how we find the equation. This is how the question will be given, right? So in the question, they will give you x of t and they will give you h of t. Then they will ask you to find y of t. And in that case, they'll ask you to find y of t. So in that case, you need not apply that convolution problem. You don't need not apply the convolution theorem. You can simply find x of s, and then you can simply find h of s, and then you can simply multiply this to find the value of y of s. Okay? And then to find y of t, simply find the Laplace inverse of y of s using partial fraction method. This is how we do the problem. Okay? So this is how the problem becomes more simpler. Okay? So suppose if they ask you to find the unit step response. Suppose if they ask you to find the unit step response, okay, so sometimes they will give you h of t and then they ask you to find the unit step response. Unit step response is nothing but finding the value of y of t when x of t is equal to u of t. This is called as the unit step signal. right? So unit step response, y of t is called as a response. So when they say unit step response, what they meant is the response of the system when the input is a unit step function. So that means find the value of h of t, find the value of y of t when x of t is equal to u of t. Right? So this is how they give you the question. Either they can define this LTI system by identifying h of t and x of t, and then they'll ask you to find y of t. Or otherwise, they will give you a differential equations. We know that every LTI system can be characterized by a differential equations. So they will give you any differential equation. They'll ask you to find the Laplace transform. So how do you find the differential? How do you apply Laplace transform to a differential equations? We know that the Laplace transform of d by dt of x of t is equal to s into x of s minus x of 0 minus, or x of 0. This is called as the initial value. This will also be given in the question. Okay, and also suppose if the degree of the differential equation is 2, in that case we write d square by dt square x of t is equal to s square x of s minus s into x of 0 minus x dash of 0 minus. See, so by applying these two equations also, by applying these two equations to the differential equation, we can finally convert our answer and make it into a frequency domain answer, and from there we can find the solution. See, so basically you can also find the solution also. Last time we learned about finding the solution of differential equation by finding the particular solution, then finding the homogeneous solution. All these methods are very difficult. So in that such a case, you don't need to apply those methods. You can simply apply the Laplace transform. Okay, that is one of the main advantage of Laplace transform. Okay.